Have you ever just looked at a mountain or maybe a weather map on the news and thought, how in the world can we describe that, all of that complexity, using just math? Well, it turns out there's a really elegant way to do it, and that's what we're diving into today, functions of two variables. So let's just kick things off with one big question. How does math describe a mountain? I mean, really think about it. How can a couple of symbols on a piece of paper possibly capture every single peak, every valley, every gentle slope? It seems kind of impossible, right? Well, that's the puzzle we're going to solve. To get there, though, we've got to start with the tools we already know, and more importantly, see why they're just not quite enough for the job. We need to move beyond a simple line and, step into a whole new dimension of thinking. Okay, so we all remember functions like y equals f of x from school, right? You can see it there on the left. It's simple. You put in one number, x, and you get one number out, y. That's perfect for drawing a 2D curve. But a mountain, well, a mountain isn't just a single path. To describe a whole landscape, as you see on the right, you need two inputs. Think of them as your longitude and latitude to get that single output, your altitude. And that's really the heart of the problem. A function with just one input basically puts you on a fixed track. Sure, you can go forwards or backwards on that trail, but you can't just wander off into the fields. To explore an entire area with all of its different locations, we're going to need a much more powerful tool. And that tool is what I like to think of as the two-input machine. This is the engine that's going to power our entire journey from here on out. It's a game changer. Now, the official name is a function of two variables. And I know, that sounds a little formal, maybe a little intimidating, but it's actually incredibly simple. Just look at that little equation, z equals f of xy. All it's saying is that there's some rule, we'll call it f, that takes a pair of coordinates, your xy location on a map, and it gives you back one and only one height, which we call z. You can think of it in three simple steps. Step 1, you pick your spot on the map. That's your xy. Step 2, you plug those coordinates into your function, into the rule, and boom. Step 3, the function spits out your precise altitude at that exact spot. It's like a perfect mathematical GPS for a mountain. All right, so we have the rule, this machine that connects a location to a height. But, a long list of coordinates and altitudes isn't very helpful. It doesn't give you a feel for the thing. So how do we go from all these numbers to an actual picture? How do we graph this mountain? Yeah, this is the big question, isn't it? We can have an equation, something like z equals x squared plus y squared. That's the recipe for our mountain. But a recipe isn't the cake. So how do we actually bake the cake? How do we turn that recipe into something we can see and explore? We do it by literally adding a third dimension. So imagine the x and y axes laying flat on a table, creating a grid, just like a map. Now, picture the z-axis shooting straight up from the middle of that table. That z-axis is our height. Now, every single point in this space needs three numbers to be located. Its map position, x, y, and its height, z. And this is where the magic happens. When you plot every single possible point, all the x, y, z combinations that follow your rule, you don't get a line anymore. You get a continuous flowing surface. You get hills and bowls and waves, all floating there in 3D space. You get your mountain. Now, drawing a 3D surface is awesome, but let's be honest, it's not always easy or practical. So, mathematicians and mapmakers came up with this totally ingenious way to get all that 3D info onto a flat piece of paper. And it all begins with slicing. So that's the puzzle, right? We have this beautiful 3D mountain. How on earth do we press it flat, like a flower in a book, without losing all that critical information about its shape, its slopes, and its peaks? The solution is just so clever. Imagine our 3D mountain is made of, a giant block of cheese. We take a wire and we slice right through it, perfectly horizontally, at an altitude of, say, 100 feet. Then we do it again at 200 feet and 300 feet, and so on. Each of those slices creates a shape, a little curve. We call that a level curve or a contour. And here's the most important thing to remember. Every single point along that one curve is at the exact same height. So if you were hiking along a level curve, you wouldn't be going uphill or downhill at all. And for the final step, we take all those slices from all the different heights and we imagine looking straight down from above and tracing their shapes onto our flat map on the table. And just like that, you've made a contour map. And these maps, they tell you so much. If you see the lines are all bunched up close together, that means the mountain is super steep right there. You're gaining a lot of height really fast. But if the lines are spread way far apart, that's a nice, gentle slope. And when you see a bunch of closed loops one inside the other, you're looking at a summit or maybe a deep basin. But here's where this idea really becomes a superpower. Because this amazing tool isn't just for mapping mountains. It turns out we can use it to map, well, pretty much everything. I mean, think about it. A weather map showing temperature, that's just a chart where the output, Z, is temperature, and the inputs, X and Y, are your location. An economist modeling profit, they can build a surface based on production cost and sales price. A CT scan is just a map of tissue density. It's the same exact mathematical idea, just with different labels on the axes. The mathematician Henri Poincaré really nailed it when he said, mathematics is the art of giving the same name to different things. In our case, that name is Z equals f of xy, and we're giving that same name to altitude and temperature and profit and density. It's like a universal language for these complex relationships. So, if there's one thing to take away from all this, it's that functions of two variables are so much more than a random chapter in a math book. They are a fundamental tool for seeing and understanding the hidden surfaces that shape our reality, from the ground we walk on to the economy all around us. And that leaves us with one final, kind of mind-bending thought. We use two inputs, an X and a Y, to map our 3D world. What if we used a function with 3 inputs? Or 4? Or 100? What kind of complex, multidimensional worlds could we start to map and understand then? The possibilities are just incredible to think about.